Okay, just like to welcome Federico, an introduction to Ceph, an architectural overview. And since we're only about 10 minutes late for the regular speaker, we'll start now. And because of the pizza, we're not going to go to the brewery after the meeting.
Sounds good. All right. So I think most of you know me already, but for those that don't, my name is Federico Lucifredi. I'm a product management director at Red Hat. I work on Ceph storage. Previously, I was the systems management czar at SUSE and the Ubuntu product manager at Canonical for 14.04. So more Linux distributions than you can count, but now we're going to talk about something different, storage instead. Now, I've had the privilege of spending almost all of my career in open source, with the exception of a stint in academia. But while open source has really disrupted all of the software space that we have, storage is still dominated by more traditional, more proprietary approaches, and this is what has driven me to software-defined space. In the cloud services area, you can think of blocks where things fit: compute, network, and storage. Ceph clearly fits in the storage box, and in our not so modest opinion, it is the future of storage. Now let's go back 1 second to the past of storage. Originally, you would record information on stone tablets, let's say. Maybe there was a chisel there. Then you would have pen and ink. But today, there are much more opaque interfaces between your data and you. Technology sits between you and your data. You can record a lot more data, a lot faster, but you also need technology to disintermediate and gain access to it. So generally, you could say that there is human-computer tape or human-computer data in some form or other. That's storage in one slide. Working through a computer means that we can store more information, we can store it more quickly, but it also means that we're further separated from the information we've created. You cannot pick the bytes of disk platters with tweezers, despite our jokes in another session here a couple of years ago. You need the hardware to decode it. And you need the software to decode it. The whole point can be expressed concisely this way. Technology intermediates the access between you and your data. And here is the second point. Everyone has seen a graph like this recently. This is what's happening with our data. There is a data explosion going on. Everything gets logged everywhere. Nobody throws away any data regardless of how much information may actually be in it. So there are scary amounts of data. And here is the old way we store this data. You connect a bunch of disks to a computer, give humans access, multi-user OS, time sharing, all of that very exciting 60s technology, or rather revolutionary 60s technology. And then, of course, it becomes successful, and the picture starts looking like this. At which point, your computer is no longer enough, and you have this picture instead. So, this is the typical scale-out problem, scaling up the system to keep up with demand. And here we see all the classic optimization problems. This sort of problem is the usual excuse to spend more money on a bigger, more powerful computer. But with the dynamics that we were describing before of lots of data, very little value in the data, you can hardly justify the economy, that the cost pattern that goes with it. So while this is a traditional excuse to justifying really expensive, costly hardware on performance grounds, this is also economically and technically broken in the face of the amount of data we have to deal with today. But here is an alternative. instead of making what you have today bigger, you can take what you have today and add many units of it. Let's call it making it broader, or properly, this is scaling out. The units remain as cheap as they were to begin with in the small scale, but you multiply their number, and you get many of them. Eventually, the industry figures out how to make appliances powered by this architectural model. You take lots of computers, lots of disks, put them in a box, and you have what's commonly called a storage appliance. You forklift it into your data center, plug in a cable, this is a storage appliance, an actual physical thing, something that looks kind of like this. And this is what's inside the storage appliance. The hardware is proprietary, not your typical Dell or HP x86 industry standard hardware. Then on top of it is software, also proprietary. And then you have your support and services contract. And as an aside, I'm going to add here the financials for the industry leader, EMC, from their latest 10K statement. The details are not important. The point that I'm making is that this is a really big business. It is maybe not as popular in blogs and publications as talking about computing, talking about OpenStack, but data is extremely important. People care about their storage a whole lot. And companies like EMC and NetApp are nothing sort of huge. The fact that their target is exclusively the enterprise, and you don't accidentally buy some NetApp like you could accidentally buy some Dell or HP, maybe excludes them more from our community circle, but the reality is that they are enormous businesses. EMC is the biggest technology business in mass today. What has happened since this model was most successful is that the cloud has started raining bits on the head of the CIO. At least that's the way I picture it. We're here today because there is an inflection point and something has to change. You cannot possibly continue to buy storage appliances at the cost that they have to store data at the rate that that we have been. I was talking to a major financial in New York about a month ago, and they were telling me that for them, storage is a $700 million a year problem. And this is not the largest bank in the US, it's one of the top 10. But that is a ridiculous amount of money just to keep around data that in many cases doesn't ever get looked at again. So here is what we propose. Here is a different model. We favor standard hardware that you already know and are familiar with. A Dell box, an HP box, a Supermicro. Open source software on top of that, and the usual enterprise software subscription on top of it, optionally, if you need it. That's where Red Hat comes in. One point that I always like to make about Ceph is that this is not a single vendor ecosystem like a number of software-defined stories that have their single sponsor. Ceph is a very significant ecosystem with SUSE, Canonical, Red Hat playing in just in the OpenStack vendor space. Hardware vendors like Fujitsu and SanDisk, and many others in between, from the large web players like Yahoo contributing code to others offering services. There are literally dozens of players in the space. Intel is a very active contributor. The result is that you are not bound to a single vendor, even when you decide to buy that support contract. If you don't like what Red Hat or SUSE is doing, you can go to Canonical, you can go to Fujitsu, and see if you get better luck with a different vendor. So that is a very important thing, because it could be open, but it could be still coming from a single vendor, and that wouldn't be enough to solve the problem. So this is what Ceph is, a much more sustainable model for storage, and this is how we built it. First, we wanted it to be open source, and this is the best way to get technology in the hands of people who can use it, to be honest, quickly. Secondly, we wanted this to be community-focused open source, not something where the source is thrown over the wall and then nobody except a single vendor is actually working with it. And the people that worked on this before the Red Hat acquisition and after, but the seeds were sown before Inktank was acquired by Red Hat, have done an exceptional job of it, and that's why I could brag about the community that we have earlier. Technically, we wanted it to be scalable, and specifically not scale up scalable, but scale out scalable, as we were going before. Think of it as if you're organizing a conference, you can look for what is the biggest hotel in town to keep your attendees, or you can have a number of different hotels to scale out the capacity of where people are going to stay during your conference. Most importantly, Ceph was designed to be self-managing and have no single point of failure. No single point of failure is extremely important because of the scale that these systems have to reach. Currently, we have customers and non-customers in production with more than 10 petabytes, but Ceph itself has no architectural limits to scale because of the way it is designed, so it can go to much bigger numbers. There may be implementation details that get in the way today. Today we're comfortable saying to a customer that they want to deploy 10 petabytes. We should be fine with that out of the box. If we want to go to 30 petabytes, we need to tune things up a little. But these are not architectural limits. These are implementation limits of today. We're going to solve them and move the bar higher. When you're looking at this kind of scale, single point of failure obviously is not acceptable. The other thing that is not acceptable is it needs to be self-managing, because a cluster with hundreds or thousands of nodes always has some failure going on in it. It's a yellow failure, so to speak. It's not something that's losing you data or bringing down the cluster, but it is something that has to be dealt with, and if the administrator has to deal with it manually, that's not acceptable. It has to happen transparently behind the scenes and just recover itself, so that the administrator gets alerts only when there is something really serious going on. Because Ceph is naturally highly available, the failures that would actually have to be raised as red alerts to an administrator would be very few. But for this to be possible, the self-managing component has to be quite smart. So that is the philosophy, so to speak. Let's go towards how it actually works. Oh, and this is a little bit of history. After 8 years of work in open source, then Inktank was started, acquired by Red Hat less than 2 years later, which brings us to today. This is essentially what Ceph is. Now, what's in it? It is a distributed storage cluster with 3 interfaces. If you need, the storage is natively object-based, but it is exposed to workloads that need to consume it in whichever way may be needed by the workload. So if you need an object interface, you go through the Ceph Object Gateway. If you need a block interface, you go through the Rados block device, RBD. And if you want a file system, you add an additional set of daemons, and you have the Ceph file system. This is the 50,000 feet view. We zoom in a little bit what's in these boxes. Here are the interfaces into the Ceph cluster with their original technical names. Let's start with Rados at the bottom. Rados is a distributed object store, and it is the foundation for Ceph. Reliable, autonomous, distributed object store, capable of self-healing and self-managing, going back to the theme that I was describing before. There are copies of your data in Rados. When a disk is lost or a node is lost, Rados makes more copies of your data into the remaining nodes or into the remaining disks, so that you are always up to a certain level of redundancy. In a certain sense, you could say that it's RAID between machines rather than RAID between disks, but it's more complicated and elegant than that. For example, you could say, you could use erasure coding and have one certain pattern of replication versus you could use 3 replicas or 2 replicas with different patterns depending on what the specific needs for the specific application are. So it's more flexible than RAID, and it's also smarter than RAID, but that is the underlying structure. Then to go into it, you have LibRados, which is a direct binding into Rados. It lets you access the object store directly from your code. So you can write an app that has directly the ability to store and retrieve data into the cluster. Or there is Rados GW, which RGW, which exposes an S3 and Swift RESTful interface to your application. So if you have an application that's coded against Amazon AWS S3, for example, you would be able to point it to a Ceph cluster through RGW, and it would be able to store information just the same. RBD is slightly more complex. It's a driver that lets you store data into the cluster as if you had a block driver interface. And Cephfs instead will give you a file system interface into the data store. We're going to go into each one by one. Here is how Rados works. So, if I have 5 disks, these could be spinning media, could be solid state, could be RAID volumes, although that is typically not a good idea. We prefer you to save your money and not have RAID to deal with in there. Lone disks are just fine. We have 5 file systems on top of those 5 disks. ButterFS, ext4, and XFS are the ones we support currently. XFS is recommended while we wait for ButterFS to get there. Then you have 5 OSDs, object storage daemons, 1 per disk, or more properly 1 per path. But broadly speaking, let's say 1 per disk. This is a software layer that makes each disk part of the Ceph storage cluster. This is a simple piece of software. You configure it with a path, and it exposes that path as a storage location to the cluster. So that is Ceph proper. Those are the bits that are bringing that hardware into the cluster. And I'm going to impose on you a ridiculous number of graphical conventions, but it actually makes explaining this so much easier. So these blocks are now called OSDs, Object Storage Daemons. Disk, file system, OSD, that's the structure that we're having. These 5 OSDs could be in the same host, or they could be in 5 different hosts. It doesn't really matter. In this case, we're saying that there is one host in the cluster that's running 5 OSDs, and that will be the graphic that we represent it with. So there are these M nodes. What are those? Of course, when you interact with the storage cluster, when you interact with the entire cluster, you don't go and talk to single nodes or figure out what node has your data manually. It looks like a giant thing, single thing. But let's break down what are those M nodes, the other type of node that you have in the Rados cluster. So the OSDs, the ones that I was describing before, there are tens to 10,000 of them in a cluster, 1 per disk. You could use Flash if you want to go to the high end of performance and spendiness, or you could use spinning disk, or you could use RAID if you want to create artificially large disks by combining multiple disks. And you attach them to an OSD. They serve the stored objects to the clients, and they perform recovery tasks. So when one of the OSDs goes down, the others are in charge to perform peering to create additional copies and recover the additional copies of your data that are necessary to maintain the targeted number of replicas. The other type of node is the monitor. Monitors control the cluster state. They know the state of each node at any given point in time. You generally want odd number of them. So most clusters have 3. One would not be highly available, and more is not strictly desirable unless you have a really large cluster, because these vote. They use Paxos to come to a consensus. You don't want too many of them having to come to a quorum. So I think in most clusters that I've seen, there are just 3, and that's fine. If you scale out into tens of thousands of nodes, maybe you have 9 of them. But the important bit that you want to remember about the monitors is that these do not serve stored objects to clients, and they are not part of the data path. So you don't have 3 bottlenecks in your cluster of 100 nodes, have 0 bottlenecks. The data always comes from the OSD. That's why I can say, without sounding ridiculous, that there are no architectural limits to scale. Obviously, if the data path was going through these, good luck, but it's not. So let's Rados underneath. All of Ceph is built on this underlying layer. The useful applications are built on top of it. So how do we build applications? Let's start with libRados. That provides you with native ability for data storage and retrieval. You attach libRados to your code, and then you can go to your cluster. What does the interface look like? Oops, I clicked one too many times. LibreOffice. No. There we go. Almost. So what's the interface like? You're writing code to talk to the cluster. You are making function calls into a library. It could be a Python library, it's C++ library, there are a few others. But you're writing custom code to talk to the cluster. If you're willing to write custom code, this is actually a pretty fun thing to do, because it gives you access to all the underlying mechanisms of the cluster. You can do some pretty cool stuff. You could also do it for simplicity, to have fewer layers between your app and your data. I believe that Yahoo, that's one of the largest Ceph users today, they are using a very large cluster of clusters that's supposed to eventually reach around 100 petabytes to store data for Flickr pictures, Flickr thumbnails, and eventually Yahoo Mail. And they structured this as a cluster of clusters to have an interesting additional layer of layouts. But I believe that they've written, in some cases, libRados code so that they could just grab the objects from the cluster without having the overhead of any additional interface. And so you can have C, C++, Python, PHP, Java, and Erlang as of the time of this writing. And obviously you have no REST protocol overhead or HTTP overhead of any kind. So perhaps Bill wants to write a Perl binding here.
I at least want to bitch about it.
All right, so.
Rico,
Yes, sir.
if the tens of thousands of devices are just undifferentiated parts of the pool, how does the application specify separation of replicas? You want to make sure that
Very good
your
question.
replication isn't all going for portions of your
That's
data.
right. You don't want all the 3 replicas to be on the same drive.
node, for instance, yeah.
That's right.
Or maybe even in the same rack, if you have a rack.
Well,
That's right.
yeah.
That's a very good question. The answer is
Yeah.
coming. It's
Okay.
a few slides down.
Okay.
When we get to the algorithm for
Two
placement.
forklift times can't get both.
So,
Question.
oh yeah, go ahead.
What's the semantics of that API? Is like something like a put get, like a.
It is an object style API, so yes. But it lets you do some interesting things. I believe that there are cases where you can say, send this code to the data, rather than send the data here so that I can process it. So for certain hacks, the Liberatos can be quite fun. But basically, yes, it's an object store API. So, built on top of Liberatos is RGW, the Rados gateway. Now, the Rados gateway provides a Liberatos interface on its southbound side, but a REST interface on the northbound side to the application. This interface is typically, well, it's always today, Swift or S3. Swift is popular in OpenStack environments, and S3 is the one that's most popular today. A significant chunk of the community and of our customers are using Ceph to have an Amazon AWS compatible object store on premise, and through RGW it looks like AWS S3. RGW could publish other protocols theoretically, but that's what it does today. The API supports buckets and accounts and a lot of the accruements that the S3 API has. It's not the complete API, we keep enhancing it at each release. It also integrates with Keystone for authentication in OpenStack environments, and it supports accounting if you have some billing or back charging requirements or anything of that sort. Usual things of a typical object store. Next up is RBD, the Rados block device. This is the most immediately interesting for those of you standing up clouds. So let's use the same graphics. Here it's how it works. If I have little bits of a volume spread across the cluster in 4 megabyte chunks, RBD will link into the virtualization layer, into KVM most often, and present those as a single disk. You can think of it as striping a volume across the nodes of the cluster and providing you with the illusion of a single volume. Now, what is the interface there? There is a Liberatos and librd. It is a library that then is integrated into KVM or QEMU or whatever else your virtualization solution is. Because the volumes are in the cluster, you can do interesting things like live migration without having to move any data. And this is one of the things that makes Ceph so popular in OpenStack. Because in a Ceph-backed OpenStack cloud, you can actually live migrate the virtual machines, the cloud guests more properly, between nodes, which is, in my view, it's something that you simply must have for maintenance purposes because the cloud can never go down. So if you're going to go with a paradigm that the cloud can never go down, you have to be able to move the workloads of your customers so that the node can actually go down for maintenance. And when you have a storage backend that requires the data to be actually copied, the volume to be actually copied to do live migration, it is not only not live migration, it's extremely painful migration. So it is not for playing at, oh, I'm going to bounce the host, I'm going to bounce my workload between machines. It's really essential for operational purposes of your cloud to be able to maintain it and upgrade the hosting nodes. there is a variation of this. Another way you can do this is via the kernel module version of RBD called, surprise, surprise, KRBD. This has been in the upstream kernel for quite a while. It mounts an RBD volume as storage, and you can mount it in dev, MKFS there, and treat it just like any normal local disk. But it's actually distributed in your cluster, giving you parallelism of reads and replication of data, which is kind of nice. It protects you if one of the drives fails. Your drive is actually replicated. It's a very robust way to store disks. This is not as popular for production environments, but it's quite cool when you're hacking something. Yeah, it's too soon to say that. Okay. Then let's go to the next one. So the RAIDOS block device, storage of disk images in RAIDOS, decouples the VM from the hosts, a powerful concept as we described. The drive is striped across the RAIDOS cluster, across the storage pool to be exact. And you can snapshot those virtual images, operate in copy on write mode. It's been upstream since 2.6.39. Ultimately, you could say that RBD is responsible for Ceph's success. I think that at the latest survey, 60+% of OpenStack deployments use Ceph RBD for storage of block data. The reason for this is that Ceph integrates seamlessly with different OpenStack projects. OpenStack Cinder for volumes, OpenStack Glance for images, Nova, the ephemeral interface for images in Nova, and it can replace Swift. So the thing that drives people to Ceph is that you can have all the storage of your cloud in a single storage cluster rather than different bits of data in different places. And then you have to either manage the different storage solutions or well, you have to manage them. So it unifies the storage silo into a single place. And we've been working to keep it that way. So we're going to add other projects like Manila and Trove as things move forward. But today the primary reason is for block, and we cover all of the block interfaces in OpenStack very well.
Question?
Yes?
I mean, virtualized environment, so it only supports the KVM because of the sort of the driver
Oh,
issue?
nice question. So there was, I believe there was integration with Xen, and I was speaking to a community manager for Citrix that was telling me that they are revamping it and redesigning it. So I don't know where the past effort is. I know that there is a new effort underway. For Hyper-V, we are not working on it, but there is a community effort underway to build a driver for Hyper-V so that that can also work. And for VMware, the way to go would be to use iSCSI that we're adding. We're working to add. iSCSI is sort of the lingua franca of block storage, if you will. So it's your catch-all default industry standard to go with in that case. So the final component is the Ceph file system. CephFS is a distributed, horizontally scalable, POSIX-compliant file system built on top of RAIDOS. This was the first of the Ceph projects, and ironically, it's the last to reach production status. We have declared it ready for production upstream in Tokyo, and it's going to start shipping in supported enterprise products next year. So how does this work? You will notice that there is a different node here, or a different icon in my diagram. File system metadata is stored in the RAIDOS cluster, just like any other data. And this requires MDS, the Ceph metadata server. Here is represented with these new squares with trees in them. Clients accessing files on CephFS first make a request to an MDS, which provides what they need to get files from. It provides the metadata associated with the file data. So again, the retrieval will be directly from the OSD, so that the MDS is not an obstacle to scale, but the metadata for that file will come from the MDS. Just like the monitors, the MDS servers are not in the data path. This design allows management of all the metadata required by a file system to happen as a separate unit, and enables scaling out the logic just like the rest of the architecture requires. The job of this component is to manage the metadata required by a file system and directory hierarchy, not to store the actual file data that is stored as Rados objects. By the way, if you are not running CephFS, you do not need to deploy this component. So you could simplify the cluster architecture if you don't need the POSIX interface. So that's how Ceph works at sort of high medium level. Now we're going to start digging into how it works at the lower level and why it's interesting as opposed to other types of storage. Before I go there, questions? Yes.
The metadata server is a district database or just a replicated database? I'm just considering that if you have a sort of really heavy metadata, heavy operations coming in, is it going to be load balanced between the multiple metadata servers or not?
It is, and we have a little bit more on that later in this. That's my third unique point. All right, so let me answer your question about how placement works by looking at how Crush works. The first thing that makes Ceph different is data placement. Let's say that you need to store some data into a whole lot of computers with a whole lot of disks. Many designs resolve this problem by placing a server that directs access in the data retrieval path, and this does not scale. There are fundamentally two approaches to solve this placement and retrieval problem. And let's call it the problem of finding your keys in the morning as you go to work. You can remember where you put your keys, or you can always put your keys in the same place. The first way to do this is to talk to a centralized metadata server somewhere, ask for the location of a given object, then it is returned to you and you connect over there to retrieve it. This one is in the fourth box from the top. Go into that pool and get it. Okay. In other words, someone keeps track for you of where the data is. This is what my colleague Ross Turk in marketing likes to call the Dear Diary. Today I put my keys on the kitchen counter method. But imagine if you were doing this at scale. This is what effectively many storage systems do, however, which is why we're talking of those intermediary boxes as bottlenecks. The other method is to split up your cluster. You have a standard coordinate frame, let's say, similar to how the volumes in the encyclopedia are indexed. And then you know that this file begins with an F, and so it is in the third box from the top, because that's how the Encyclopedia Britannica works. But there is a but. This is what we call it, let's always put the keys on the hooks by the door with numbered spots. Cute, but what happens when this house of yours is actually changing? Your house is infinitely big and always changing. There are machines coming in, nodes going out, it's growing in scale, it's possibly shrinking. Where exactly are your hooks by the door here?
Sounds like you described my cars.
So there is a problem with just saying it's always in the same place. So we have to algorithmically find it. And the answer is what we call the crush algorithm, controlled replication under scalable hashing, which is where your storage starts to look more like a peer-to-peer sharing program than traditional big vendor storage. So if you know distributed hashing algorithms, this will look very familiar. Crush is an algorithm, and this is how it works. The first thing we do is we decide what placement group an object belongs to by hashing that object's name. Then I'm going to run the crush algorithm on that placement group. I'm going to pass it the cluster set and the rule set. And based on that, the algorithm is going to decide where the data lives in the cluster. The calculation is performed on the client. You do not need to talk to anybody to get your data's location. You calculate it based on the rule set and the cluster state that you originally retrieved from a monitor. That's what the monitors are there for. They're going to give you the state of the cluster, so when something changes in the cluster, they are in charge of letting you know and giving you the new cluster map. So if you follow this process, you can place all your data in the cluster, and we have our starting point to see how things work. So, our boxes are getting a little bit more complicated. Crush, which now will be represented by this icon, is a pseudorandom placement algorithm that is very fast to calculate. It requires no lookup and is repeatable and deterministic. It will produce a statistically uniform distribution of data. There won't be exactly the same amount of data in each one of your nodes, but close. Obviously, it's repeatable, or you would never be able to find your data again. It is a stable. Maybe in some cases. It is a stable mapping, so when something changes in the cluster, the impact to that is limited. Let's say one node in the cluster goes down, the impact of how many things need to relocate will be 1 over the number of nodes. It's not going to be everything needs to shuffle everywhere. And it supports rule-based configuration. So you can introduce rules that are topology aware, like what the gentleman was saying. Do not put 2 of these copies in the same rack, or in the same machine, or in the same room, or whatever arbitrary rule you want to establish. So you can insert additional rules to the mapping. It's not just a straight distributed hash table. So this is now how we make the graphic look, if it loads. So let's say a client needs to find a piece of data. It runs the algorithm and finds that there are 2 copies, there and there, without asking any intermediary. And of course there is a bug on the slide because those 2 boxes should both be green, but just or both be blue. Anyway, let's work with what we have. This cluster is a 2-replica cluster. Usually Ceph clusters are 3-replica clusters, but this makes the graphic a little bit less busy. Meaning there are 2 copies of each piece of data, and if one node goes away, the other copy is still there to save you, and the cluster will make a second copy of it as soon as it detects the failure, so that it goes back to the level of resiliency that you specified of 2 copies. While we're on this topic, most common configurations for resiliency are 3 replicas. That's the most common one for RBD, the block device. The other one that's common is erasure-coded for object storage with RGW, where performance is not so touchy and you can save a little bit of space instead of using 3 times the space in terms of having 3 copies. You get away with 2 point something. Okay, so this is how Rados works, and I think there is a slightly more detailed slide. So here is how it really works. Let's say you have an object with the name foo assigned to the bar storage pool. First, I'm going to hash foo and decide that based on its name, it belongs in placement group 23. Then I combined it with the bar pool, which is just 3, and I pass 3.23 to the crush algorithm. The crush calculation then tells you what your target OSDs are, and then off you go. In this case, these are 3 replicas, so it goes to those 3 OSDs. It goes to 1, and then the first OSD takes care of the replication into the other 2. This all happens on the client in libraries. Your code is obviously not doing any of this. We're just explaining so that you know how the cluster works. This is how it works underneath. You are not calculating the placement. But what happens when something goes wrong? So let's say I have this cluster, I have 10 nodes, and I lose 1. What happens? The OSDs are watching and working cooperatively. They get information from the monitor nodes that have voted and decided that that node is out and not down. In Ceph terminology, in and out means gone forever, up and down means gone temporarily. So that that node is gone, isn't seriously gone, somebody vaporized it. How are we going to go back to retrieve our red and yellow boxes that were replicated there? The cluster rebalances the placement of the data and creates new replicas. So red belongs there and yellow belongs there, and we create new copies. Now if I have 100 nodes and lose 1 node, the amount of data that moves is 1/100th. So 1 over n of the number of nodes, which is what we were saying when we were talking about stable mappings. As this is a many-to-many movement, it's also quite efficient. It's not like one node is in charge of all this replication. Then how do we find the data? Now, the clients, having received the new cluster map, know to look at the new locations to retrieve the data because they are running crush with the new cluster map. This algorithmical placement that comes out of a formula looks a little bit like magic if you are not familiar with distributed hash tables. But this is effectively how peer-to-peer systems so popular in the last decade work. This is how a peer-to-peer network knows, oh, I'm looking for this file, which one of the many nodes in the network has the file. The thing that's added on top of the distributed hash table are those rule sets that Crush has that allow you to specify rules like I don't want them in the same rack or additional constraints of that kind. Even if you know the algorithm, it still looks a little bit magical, but I guess that's cool. Now, one other thing. This one is interesting in an OpenStack context. So we go back to the picture where we have KVM mapping back into Rados to get the image that's backing up our virtual machine. How do we spin up VMs efficiently when we have many? I need 10 new copies of my CentOS 7 VM. I had my original image. I want to spin up 10 of them. Am I going to make 10 copies of the original image? Aside from the waste of space, the other thing that matters is you have to wait, and you don't want to wait. When you're launching a new VM, you want to have satisfaction immediately. You want it to be immediately starting up. So this is resolved with layering. intricate slides, so it takes a while to load. Let's say we have a volume with 144 arbitrary units of storage. With RBD, you can copy these images as many times as you need, and it will take no additional space until you start writing to them. So let's say that we want to spin up 5 VMs. We'll make 5 copies of the original image because it's mapping back to exactly the same blocks in Rados that constituted the first image. There is 0 additional storage that's being taken up. But when the VMs start writing back into the image, then the delta is going to start accruing, meaning those blocks will not be transparent mappings anymore. They will start to diverge from the original. And you're going to start consuming a little bit more space. And the same happens with reads, which are going to come from the new map, if there is anything in it. Otherwise, they're going to go back to the master image. This is what's usually referred to with terms like copy on write or thin provisioning, or it has a number of different names depending on what the technology is. In the case of Rados, it's not really copy on write literally. That's why we call it thin provisioning, but it's pretty much the same result when you think of it. It is extremely powerful and makes your use of storage very efficient because you don't have to wait for copies, and efficient because you're not creating redundant copies in the first place. So this is something that is significant enough in OpenStack that people make demos of how fast you can copy. You can implicitly copy from a snapshot and start up a new VM. I would consider it a little bit table stakes, but I guess I'm privileged because I have that functionality. Suppose it's not so for other storage systems. In any case, it's cool because when you spin up a new VM, you don't need to wait for replicas. Now, the third thing is how Ceph takes care of metadata. So we were talking before about the fact that we need to have all of the metadata to give out the illusion of a POSIX file system when the data is actually in an object cluster, if you want POSIX interface. So there is an interesting problem in partitioning the metadata on a cluster. MDSs store all of their data within Rados itself, and they work in a scale-out fashion like the rest of Ceph. But here is a problem. If we have one authoritative server, so here is the problem. There are multiple MDSs. And if we have one authoritative server for the entire metadata space, then it's easy to understand how it works. But we cannot have just one, because that would be a terrible idea. We want high availability, we said at the beginning. The cluster can take the loss of multiple nodes, multiple disks, and still have all of your data. The only scenario where you need a second Ceph cluster is if you want a disaster recovery configuration where the entire cluster got wiped out as opposed to losing a few nodes or a few hosts. So these guys need to be HA, therefore there must be more than one. So how does it work? If the slide loads, I can show you. So one tree and multiple servers. When you start with the first one, when we start with one, as I was saying before, it's very simple and very obvious. Obviously, the one server is taking up the entire tree, and it's not highly available, but it's simple. Then when we add a second, When we add the second server, it's going to look at where the load is going into the cluster, and it's going to try to grab approximately half of the load by partitioning the tree in a single place. When you introduce your third server, a similar process takes place, and it tries to, again, equalize the amount of work that the servers are doing by taking another chunk of that. It gets to the point where if you have a sufficiently high number of MDSs and you have a file that's seeing a lot of traffic, you could have a metadata server dedicated to just a single file, so that even though it's a hotspot, its performance is not affected just by the fact that you need its metadata. I think LibreOffice is dying, but let's see if it can give us the last bit. There we go. Okay. So now we are done with the animations, and hopefully it's going to move faster. This is what's called dynamic subtree partitioning, by the way. It all happens dynamically based on load and the structure of the data. And CephFS has been the last one to arrive on the scene in terms of Ceph supportability, but it's in use already in the community, and it's coming to an enterprise support level next year. So it's going to be interesting to see what adoption it receives. In OpenStack, the file service, Manila, has almost zero adoption. So ironically, the fact that we're going to make Ceph support the file service might increase the adoption of the service rather than the adoption of Ceph. But it is going to be interesting to see what people actually do. Here are a few resources about the project, how to get started, how to build your first cluster, and there is a quick start guide at ceph.com QSG. The bits are at ceph.com/get. You can start a test cluster using Ceph Deploy, the tool that we make for easier configuration than actually building the cluster bit by bit by hand. You can use Juju and deploy on Ubuntu using their orchestration system. You can use Ansible. You can use Puppet. I don't know what state the Chef recipes are in, but there are Chef recipes as well. So there are really a lot of ways to build the initial cluster. And of course, there are lots of docs. If one wants to get involved in the project, there are the usual set of community resources, IRC, Upstream, Backtracker, doc writing documentation in case someone wants to start with writing docs. And it's an interesting group because unlike other open source projects that are very much a monoculture of a single open source vendor, Ceph has different hands in the pie at all times. It's a little bit more like the kernel than other monoculture open source projects. So we work a lot with Intel, SanDisk, Fujitsu, for instance. SUSE has other partners, and they're also working on it. Canonical ships their own. There is quite a bit of activity coming from all directions, so there is always something interesting going on. This is my contact info, which you all have from past talks anyway, but just in case. Are there any questions? Did this make sense? Was it an okay introduction?
I'm curious, will this work well for home use?
It depends.
Actually, let me describe what I'm doing at home right now, which is seriously needed some improvement. Right now, I have a lot of data on a bunch of Western Digital network drives, access we had at best, and there's no RAID and no redundancy there.
Mm.
And I don't have a backup solution for that yet. And I was thinking of a bunch of cheap devices, so with a Raspberry Pi, doing some kind of like redundancy would be a big improvement. I'm wondering if Ceph would be a good solution for that.
So it depends on multiple fronts. So from one side, if you're going to go with a traditional solution with that, which is you're buying a single expensive box that's RAID, or something fancier like a Drobo maybe, that's RAID and something. Obviously you have the cost of the acquisition of the hardware, and usually you also have the fact that all the drives have to be the same thing. With a software-defined solution, obviously you can have Ceph and use very different computers and try to combine them in a single cluster. I think that as long as you don't have a precise performance baseline that you need to hit, that would be fine. But there are also simpler ways. So Ceph is an enormously configurable system. But if you don't need a block interface and you don't need the object interface, you just want files, there is Gluster, which is a simpler project and it's simpler to deploy. And it may not have the scale of flexibility, but it's much simpler to deploy if you just want to scale it out, replicate that.
Moose FX also.
Moose.
Moose FX.
I mean, how much data do you have? I mean, it sounds like for like a home use, I know a lot of people just buy like a Synology and put it at home. And
I have about 18 terabytes of data on the Apple servers. I maintain a lot of metadata and text files within various directories, and I've got shell scripts for managing that. And then for several applications, I have some cron scripts run every night. Each NAS runs fine on its file system to create a text file. And then there's a bunch of scripts on one of my servers that sucks all those in, processes them, and imports them into a PostgreSQL database.
Well, I was saying earlier that nobody's throwing away any data ever.
Yeah.
Jerry.
Okay. One question I had earlier, when you lose a node, how does Ceph go back to having having the data on 3 separate nodes?
Right.
Obviously, it's using the metadata.
So let's take the scenario where you're using 3 replica. So you have a certain number of nodes, let's say 10 nodes in the cluster, and there are 3 replicas of your data in the cluster. There are 3 copies of the data. When you lose a node, 1/10 of your data is gone. The system knows which replicas of the data were located on that node. When the monitors vote and decide that node is gone for good, and they update the cluster map, then the OSDs will start recovery for the data that was known to be in the lost node. They still have 2 copies of that data. So they can very easily make a copy from the data that they have. What they need to figure out is where will this data go. Now, usually with distributed storage systems, you don't want to run the cluster at full or near full because performance degrades. There is space in the cluster. The nodes always have space available. So finding space is not a problem. It's just the algorithm updates the placement because the cluster map changed. So the OSDs that have the data that now is no longer at the 3 replica state will start replicating to the new location that is as of yet not copied. And that's why it's a many-to-many copying, because the OSDs themselves are taking care of creating the replicas.
I mean, it seems like any node that data is not on is eligible to take it, like the green
Right.
block. Any node that the green block is not on as a replica already is eligible for that green block to go on.
Theoretically, yes, but it's algorithmic, so really only one node will get that copy based on the algorithm. But the space is there in the
Yeah,
cluster.
but like there's the 7, the remaining X, so if you got 10 and 1 dies, the blocks are on 2 of them. Like any given block is on 2 of them. So there's no point putting that same third copy on those two machines.
Oh, yeah, of
Those
course.
would have to be eliminated immediately,
Right.
because that's stupid.
Right. Those would not be selected.
Yeah.
When a node dies like that, how does the system alert you that you need to replace it? Do you go through an email or Nagios or something?
That is what a third component does, and that is sort of more vendor-dependent solution. Inktank maintained a project called Calamari that was a monitoring and management UI. So you would see a map of the cluster and you would know these yellow failures. There is a drive that's failed in this machine, or this machine is completely gone, go see what's going on. I think it's fine that there are interfaces that are being developed by several of the major monitoring companies, and I don't think that they're out with them yet, so I probably shouldn't say who they are, but there are top 3 names, so you know who they are. The thing that we're trying to do upstream in the community is that we would like the interface to the cluster to be a single interface for everybody, so that you are not looking at the Ceph cluster significantly differently if it's a SUSE cluster or Red Hat cluster or somebody else's cluster. So the Calamari interface is going to be thinned down and it's going to be baked into the monitor interface of Ceph, so that it's always there as a RESTful API to managing the cluster. And that's going to happen at some point next year. Really, the problem is not figuring out that the nodes are out or that you need to do something, because there are more monitoring solutions out there than you can imagine to do it. The problem is, if you don't have a monitoring system that is cluster aware or designed for a distributed system, the monitoring system will just give you alerts all the time. It will be, there is a drive failure here, this machine is on fire, and you will get lots of alerts. With a large cluster that has thousands of nodes, you will get constant alerts. And that's why you need monitoring that's cluster aware, and it was designed for a distributed environment so it can distinguish. This drive has failed, it's dead, but it's okay, versus 5 machines are on fire. This is probably something that I should look at. Traditional monitoring systems cannot drive that distinction. Everything is, so to speak, a red alert. So you want something that's more cluster aware, I guess is the word. OpenStack is the same problem. Anything that's horizontally scaled will have the same problem. You need a monitoring system that's intelligent enough to know the higher level interface.
When I say cluster where I mean like it needs to like calculate how many certain threshold with number of drives is dead.
It could calculate. It could calculate. It could know the architecture and do the calculation itself. In my ideal world, you have the cluster exposing that information to the monitoring tool, so that you don't go into the scenario where different vendors are telling you different things about the same problem, which comes back and bites you later. But you could do it both ways. Yes?
Does it try to get the data off the node that's closest or fastest?
Not really, because you don't really know where the data is in the cluster. So that is not something that Ceph does. If you look at the scenario where, let's say, you're co-locating, let's say you're looking at vSAN. Are you familiar with vSAN? All right, never mind. Let's say that you have an OpenStack compute node and you put a Ceph OSD node there. Even if you're asking for the data based on the fact that you have an OSD there, the data is going to come from the cluster wherever the data is, because it's algorithmically placed. There are some systems where the data can migrate in the cluster so that it's close to where it's being used. So when you're co-locating your software-defined storage with your compute load in the same machine, the data is going back and forth in the same machine. And this can happen transparently, just based on use. I think that there are a couple of vendors that do this. Ceph doesn't do that, at least not yet. Alrighty,
Thank you.
I forget the name, Harvard man.
Peter, yeah, no,
Peter.
just wanted to know about, we've heard some talks on Gluster and how, I mean, is the Ceph basically, is there any reason that you would want to use Gluster if you could use Ceph?
It is not that straightforward. So what does Gluster have? Gluster has the fact that it's simple. So if Gluster is enough, as I was saying to John for file, if Gluster is a reasonable solution to your file-based problem, you can use Gluster just fine, and it's probably simpler for you to build a cluster in the first place. Ceph is interesting because you are unifying your storage. Instead of having many storage silos all over the place, you have just one that's inherently highly available. Ideally, you have a single storage administrator, and unless you have concerns like, well, I have to have a second site in another city because by regulatory requirements, if the city disappears, I still must have my data. You don't have any concern because the thing is inherently highly available. So you're bringing in additional complexity, but you have a lot of payoff for it. Gluster's trump card is its simplicity for file use, and I would say also its maturity for file use. Ceph is starting to trot in the file space, while Gluster has been in the file space for a while. So if you're an enterprise kind of user and you have these checklists with hundreds of things that you want, and then you're in the usual situation where you could run the checklist and look at Solaris and look at Linux, and Solaris looks like a better solution than Linux because it's been around for 30 years and it has more boxes checked off. And without going to that extreme, when you're looking at storage solutions, Gluster is farther down the maturity curve for file, so more of those checkboxes are set.
And what kind of I mean, in terms of your usage monitoring, what kind of interconnects? Are most people using Ethernet or InfiniBand, or what's the
The typical interconnect is two 10 gig E. All right. Yes.
Is there like a, so if you were going, let's say you had 10 nodes, is there a recommended unit of, let's say, scaling? I know sometimes when we, like, I've come from an enterprise place that uses enterprise storage shops, and they're usually like, for performance, you should add a whole tray at once, kind of thing, because of, now it's got twice as many disks. I can see like you add one node, so instead of now 10 nodes becomes 11, to get the 1/11th of the data, all that data has to replicate into one, things have to replicate into one node. And that one node would probably be the gating factor of the rebalancing, because how quickly can it accept data from 10 other nodes
Well,
in order to rebalance. So is there like add 2 at once, 5 at once?
the rebalancing doesn't affect your cluster. I mean, your cluster is still available during the rebalance.
Yeah.
What you don't want to do is cause a massive rebalance where it's actually affecting the performance of
Yeah.
the cluster, right? So in terms of sizing at the low end, if you have 10 nodes, adding one node, I don't think that's a problem. At the very high end, you get scenarios like Yahoo, where I was mentioning the supercluster. Instead of running one cluster, they run it as a supercluster, because this way they have multiple clusters and they add entire racks. So when they add a rack, they don't cause a massive amount of replication. It's bounded to that subcluster, so to speak. So there are different levels of where your trouble could be, and it's kind of specific to your scale. At the low end, where you have 10 or 12 nodes, I would say adding one node is certainly fine. That's not a problem. I wouldn't double the size of the cluster all of a sudden, so you have half of your data moving around. Or I would if it's Saturday and I can wait.
Yeah,
There
it
is-
seems like if the cluster was, let's say, mostly full, and you had one node, well, obviously all the replicas can end up on the empty one. So, because there's no real room on the rest of them to store additional replicas, you kind of have to wait until.
Well, what is going to happen is that if you have 10 nodes and they're nearly full, when the moment you add the additional capacity, 10% of what's in there is going to
Yeah.
migrate. So you can kind of guesstimate what the amount of traffic will be because you know how much is in each node. The other thing that you can use as rules of thumb is whether you want to go for massive performance or for cheapest capacity. So today you can have 60 drives in a single system. If you use 60 drive systems, obviously the performance is not going to be the highest, but the cost per gigabyte is going to be the lowest. I have a colleague that likes to call this cheap and deep.
Yeah.
For reasonable performance, the sweet spot is between 12 and 24 drives per system. That's what we recommend.
Thank you.
Oh, there is one more.
So how does Ceph deal with heterogeneous device types?
As a heterogeneous device,
Heterogeneous device types. I want my hot data on my SSD drives, I want my cold data on some SATA or.
there are two things for this. One is there, and the other one is in development. So one is that we have an abstraction called the storage pool. Your data doesn't just go into the cluster, it goes into a pool in the cluster. So you can control some of the placement with the pool. You could say this is an SSD pool, well that is a spinny disk pool, and decide what data I'm writing to where. That is what you can. I'm
The
sorry?
application does that, not Ceph.
The application decides, the application announces what pool it wants to write to. That is what you can do today, which obviously brings the next problem, which is what you were hinting at. The data may be changing hotness and want to migrate between these things. So we have a system that's called cache tiering right now that's been in technical preview for a while. We're going to dedicate this facility, or at least currently the thinking upstream is to dedicate this facility to tiering and use another solution for caching. Cache tiering would the current implementation of cache tiering would then effectively be what is in charge of migrating data between pools based on a set of rules. So if you look at what we refer to as cache tiering in our current documentation, an evolution of that is what's going to take care of the migration.
On the Red Hat website.
On the Ceph website, on the Red Hat website, either way. All right. Okay.
Thank you.
Thank you.